Dear students, after studying this module, you shall be able to understand the correlation between the conformations and reactivity, elucidate the stability of the product with the reference to conformation of the reactants, analyze the Curtin-Hammett principle, various conditions of the Curtin-Hammett principle and its application along with the Weinstein-Eliel rate equation. The conformation reactivity relationship is very essential in understanding the stereochemical aspects of product formation. Dynamic stereochemistry concerns with the stereochemical studies of any rate process involving bond making and breaking of bond or interconversion of the conformers. This depends upon the stability of the conformers. The relationship relates the stereochemistry of the starting material and products in respect to the transition state. Conformations of the starting materials play a vital role in the reactivity. Barton in 1950 first time established the relations between the conformation and stability and reactivity of the alicyclic compounds. Conformational studies of the important substrates are considered in the following sections. Conformational studies of the substrates. Let us look into the conformationally rigid diastereomers. There are cyclic molecules whose groups which are reacting are connected into two different orientations. The axial and the equatorial proportions provide a direct relationship between the conformation and reactivity. Compounds with two or more cyclohexane rings link through trans ring junctions and does not undergo ring inversion are rigid towards reactivity. For example, in trans 2 alpha decalol as shown in the figure 1, the OH group is present at the equatorial position, while in trans 2 beta decalol, which is represented by the figure 2, the OH group is present at the axial position. When these two conformers are subjected to acetylation, the trans 2 alpha decalol reacts faster than the beta isomer. Conformationally mobile diastereomers, those molecules which exist in the erythro and thioisomeric forms come under this category. In this example, the relative specific reaction rates of the two diastereomers depend upon the respective rates and their population in the equilibrium mixture of each of the diastereomer. For example, in 2,3,4 triphenyl butyric acid, which exists in two diastereomer, thio and erythroform respectively. Thio is the preferred conformation having the carboxylic group very close to the benzylic group, that is CH2 phenyl group at C4 carbon atom. It cyclizes with anhydrous hydrofluoric acid mainly to give tetralone as shown in the structure 1, while erythro having the carboxylic group very close to the phenyl group at the C3 carbon atom cyclizes with anhydrous hydrofluoric acid mainly to give indenone as represented by the structure 2. Henceforth, the different diastereomers are finally giving the product which are two different products. Single substrate with two or more conformers. The overall specific rate of the reaction, which is represented by K, of the substrate in mobile equilibrium rely on both the ground state population of the conformer and on their specific rate of reaction as stated in the equation as follows. The equilibrium constant is the summation of mole fraction of the ith conformer and the specific reaction rate as shown here in the figure. K is summation of Ni Ki, where Ni is the mole fraction of the ith conformer, Ki is the specific reaction rate and K is the overall specific reaction rate. Quantitative correlation between the conformation and the reactivity has been explained by two principles. These are Curtin-Hammett principle and Weinstein-Eliel rate equation. At one time, these equations extensively used to find out the conformational free energies. Together, the Curtin-Hammett principle and Weinstein-Eliel rate equation gives a quantitative analysis of the conformation reactivity relationship. Let us look into the Curtin-Hammett principle. Curtin-Hammett principle is applicable to the systems in which formation of different products takes place from the substrate, which occurs in two different forms that are in equilibrium with each other. The quick interchanging reactants can be enantiomers, diastereomers or constitutional isomers, but formation of the product need to be irreversible and different products formed must be unable to interconvert or they must be in non-equilibrium. Curtin-Hammett principle defines that in a chemical reaction, if the product formation from one conformational isomer and another product is produced from the another conformational isomer which are rapidly interconvertible, then the composition of product is not totally dependent on the respective proportions of the conformational isomers in the reactant. The ratio of the product is measured by the difference of the standard Gibbs energies of the corresponding transition states. The reaction may progress through minor conformation if it is the one that provides the admittance to the low energy transition state and is completely independent of the difference in the ground state stabilities of the conformers. For example, let us look into A and B, which are two distinct conformers of the substrate S, which are in rapid equilibrium with each other. Conformer A irreversibly converts to C, while the conformer B irreversibly converts to D. But products C and D are not able to interconvert as shown below. Here, K is equilibrium constant between conformers A and B, and Kc and Kd are the rate constants for the formation of the products C and D respectively. When K is larger than either Kc or Kd, then corresponding to the Curtin-Hammett principle, the product ratio, that is C is to D, is not equivalent to the reactant ratio, which is A is to B, but is defined by the relative energy of the transition states. K is larger than either Kc or Kd means that the rate of interconversion between the substrates A and B is much faster than the rate of formation of the products C or D. If both the reactants that are A and B are at identical energy, then the reaction will relate on the energy of the transition states only leading to the products C and D. However, if both the reactants A and B are at different energy levels, having low energy barrier for the interconversion, then the distribution of the product is determined by both the relative quantity of A and B and the relative barriers to the products C and D. The reaction coordinate free energy profile is depicted by this scheme as follows. Here, it can be very well seen that the ratio of the product depends upon the free energy delta G. Here, C will be the major product having lower delta G for the transition state C, while product D higher delta G for the transition state D. So, formed is less amount. From this, we determine that the distribution of the product lies on the relative free energies of the reactants A and B. Various conditions for the Curtin-Hammett principle. Let us look into the various cases. In the case 1, the major product formed is formed by the less stable conformer, or less stable conformer reacts quickly than the more stable conformer. The less stable conformer is at a higher energy and thus it is present in the less concentration at the room temperature. Conversely, conformer which is more stable is at a lower energy and thus it is present in the higher concentration at the room temperature. Here, the less stable conformer reacts faster and gives the product because of the low free energy delta G of the transition state. For example, tropane is a 3,2,1 bicyclic nitrogen containing organic compound. This is a bicyclic amine having pyrrolidine ring on one side and the piperidine ring on the other side. This given molecule occurs in the two conformational forms. Conformation having methyl at the equatorial position is more stable than the conformation with the methyl group at the axial position because of the steric hindrance. They are comparatively more hindered sterically on the side of the piperidine ring than on the pyrrolidine ring side. Tropane on alkylation with methyl iodide forms major product from the less stable conformation. Here, relatively the conformer that is less stable reacts through more stable transition state to give the major product. Therefore, the ground state conformational distribution does not show the distribution of the products. In the case 2, when the major product is formed by stable conformer or more stable conformer reacts faster. Conformer which is more stable is at a lower energy and it reacts faster to form the products through the low free energy transition state. Here also the product distribution does not show the equilibrium conformer distribution. For example, diastereomeric conformer of 4 tertiary butyl 1 methyl piperidine in which both the methyl and the tertiary butyl substituents are at the equatorial position is 3.16 kilocalories more stable than the conformer in which the methyl is at the axial position and tertiary butyl substituent is at the equatorial position. Here the conformer of 4 tertiary butyl 1 methyl piperidine which is more stable leads to the formation of the major product with the product ratio as 95:5. It is very clearly depicted here in the given structures that how the reaction takes place with the more stable conformers. In the case 3, if the rate of the reaction is same for both of the conformers, the two different conformers which are in equilibrium with each other react at the same rate over the transition states having the same energies. In the given case, the selectivity of the product formation then depends only on spreading of the ground state conformers. For example, in cyclohexyl iodide which reacts with the radio labeled iodide and forms both axial substituted and the equatorial substituted products through the same transition state. Hypothetically, both the products should form 1:1 ratio, but this is not the case. As can be seen here in the given structures, the hypothetical product ratio is 1:1. However, the product equilibration precludes the given observation. Application of Curtin-Hammett equation. Application to the dynamic kinetic resolution. Kinetic resolution is used to differentiate between the two enantiomers in the racemic mixture. For example, if two enantiomers SR and SS are allowed to react with the chiral catalyst or a reagent in a chemical reaction, then they react at the different reaction rate and results in the formation of an enantiomer enriched sample of a less reactive enantiomer. The less reactive enantiomer is further separated from the products as it is shown here in the given equation. The starting material with the two conformations R and S in the presence of the chiral catalyst forms the product with the conformation R, whereas the starting material with the conformation S is retained and then finally separated out. This enantiomeric excess, also termed as EE, of the starting material which remains unreacted continuously rises as more of the product is being formed, attaining finally the 100% just before the completion of the reaction. But dynamic kinetic resolution is a kinetic resolution where 100% of the racemic mixture can be changed into 1 enantiomer. Dynamic kinetic resolution, that is DKR, is an illustration of the Curtin-Hammett system in which the composition of the products is calculated by free energies of the transition states and not the composition of the preliminary materials. It is used in the asymmetric synthesis. Dynamic kinetic resolution uses a center of specific molecule which can be easily epimerized so that the R and S enantiomers can interconvert during the reaction process. At this particular point, the catalyst selectively lowers the energy of the transition state of a single enantiomer, giving just about 100% yield of one reaction pathway over the other. Let us take the racemic mixture having both the R and S enantiomers. When this racemic mixture is subjected to a reaction using a catalyst, then it is selectively lower transition energy of R enantiomer, leading to almost 100% yield of one enantiomer R as a product over the other as shown. DKR is useful in Noyori's asymmetric hydrogenation. It is a chemical reaction in which ketones, aldehydes and imines are hydrogenated enantio selectively using a chiral binap ruthenium catalyst. The R form of the binap ruthenium catalyzes the synthesis the R product and S catalyzes the synthesis of the S product with the high enantiomeric excess. Rapid equilibration between the enantiomeric conformers and the irreversible hydrogenation place the reaction under the Curtin-Hammett control. The use of a chiral catalyst results in the higher energy and a lower energy transition state for the hydrogenation of the two enantiomers. The transformation takes place via the lower energy transition state to give the product as a single enantiomer. Consistent with the Curtin-Hammett principle, the ratio of the products is dependent on the absolute energetic barrier of the irreversible step of the reaction and does not reflect the equilibrium distribution of the substrate conformers. The relative free energy profile of one case of the Noyori asymmetric hydrogenation is shown here in the given equation. In the example, a beta keto ester exists in two conformers 2 and 4, which are in equilibrium with each other. The chiral catalyst R binap ruthenium lowers the energy of the conformer 2 in comparison to the conformer 3. Thus, conformer 2 reacts faster and exclusively forms the 100% of the product 1 rather than the 5. Application of regioselective acylation. Curtin-Hammett principle is used to explain regioselectivity in the acylation of 1,2-diols. Usually, the least hindered site of a asymmetric 1,2-diol undergo esterification faster due to the least steric hindrance between the diol and the acylating agent. But Curtin-Hammett principle is used to explain selective esterification of most substituted hydroxyl group in the synthesis of carbohydrates and other polyhydroxylated compounds using stenylene acetals as shown. The asymmetric diol is first treated with the tin reagent like dibutyl tin oxide to produce dibutyl stenylene acetal. This compound is then reacted with one equivalent of the acyl chloride to give the stenyl monoester. The two isomers of the stenyl ester are now available and can go through the rapid interconversion through the tetrahedral intermediate. Primarily, the less stable isomer prevails as its formation takes place more quickly from the stenyl acetal. However, letting the two isomers to equilibrate gives an excess of a more stable primary alkoxysteinane in the solution. The given reaction is then quenched irreversibly. with less hindered primary alkoxystannane reacting more quickly. This gives the selective production of the monoester, which is more substituted. This is according to the Curtin-Hammett principle, in which the more stable isomer reacts more quickly. Application to the asymmetric epoxidation. Pen-3-ene 2-ol shown in the figure 1 is a chiral allylic alcohol which exists in the two conformations number 2 and 3. It undergoes diastereoselective epoxidation by titanium peroxy complex to form major product as 4 and minor product 5 via the transition states 2 and 3 having 1.43 kilocalorie per mole difference in the transition state energies between the two conformers. The experimental product ratio is 91:9. Weinstein-Eliel equation rate. It compares the overall specific rate of a reaction K of a substrate with the specific reaction rate of the individual conformer irrespective if the products are equilibrating or non-equilibrating. For example, trans 4 tertiary butyl cyclohexyl tosylate does not go through E2 elimination, since the equatorial conformer cannot have the tosyl group anti-periplanar with the adjacent hydrogen atom. Alternatively, cis 4 tertiary butyl cyclohexyl tosylate undergoes E2 elimination with the specific rate of 7.1 into 10 to the power of -3 liter per mole per second. Let us summarize. The conformation reactivity relationship is very crucial in understanding the stereochemical aspects of a product formation. Curtin-Hammett principle is applicable to systems in which different products are produced from a substrate which exists in two different forms which are in equilibrium with each other. The quickly interchangeable substrates can be enantiomers, diastereomers or constitutional isomers. Curtin-Hammett principle is useful in the dynamic kinetic resolution. Kinetic resolution is used to differentiate between the two enantiomers in a racemic mixture. Curtin-Hammett principle is also applied in the asymmetric epoxidation. Curtin-Hammett principle is used to explain regioselectivity in an acylation. Noyori's asymmetric hydrogenation is also dependent on the Curtin-Hammett principle. Weinstein-Eliel rate equation associates the overall specific rate of a reaction, which is K of a substrate, with the specific reaction rate of the individual conformers irrespective of the fact that if the products are equilibrating or non-equilibrating.